Here in section 11.2, we're not really going to do anything that's different necessarily than the previous sections. They're just going to be not quite as nice. So in the last section, it was just a single series for the first order and the sine and cosine. So this one is going to be a bit more reliant on the recurrence relation. So here we have an example that is y double prime minus 2x y prime plus y equals 0. Again, let's recognize that this is not one of the ones that we know how to do, and so this is new to us, okay? And here's one that we can solve using power series, or we can get an approximation using power series. So let's find some power series solutions to this thing, okay? Now, let us begin with our y equals, oops. So y is going to be our generic n equals 0 to infinity, a sub n x to the n. Then y prime is going to be n equals 1 to infinity, n a n x to the n minus 1. Then y double prime is going to be n equals 2 to infinity, n minus 1, a n x to the n minus 2. All right, so we're going to write that in almost every problem. Now we're going to substitute all of those back into the original. So back into this, and so we write the first one, 2 to infinity, n minus 1, a n x to the n minus 2, minus 2x times the middle one, plus the last. And again, this equals 0. So the first thing we'll do is send in all the stuff, right? So send in that, and what do we get? We get plus 2n. Let's leave it minus. Doesn't matter. Minus 2n a sub n x to the n plus 0 to infinity. All right, so these two are both in terms of x to the n. Let's write this in terms of x to the n also. So this needs to go up 2. So that'll be n plus 2. That will be n plus 2, n plus 1. And then that'll go down to 0 to infinity. What now then? So this one is the one that's different, right? It starts at n equals 1. We have to sort of peel one off, but you can't peel one off. These are the ones that have the one that need peeled off. So we're going to have to peel off the 0 term here and the 0 term here, so that way they all start at 1. So when n equals 0 on this one, I have 2a2 x to the 0 plus a 0, right? 2a2 plus a 0 on that. Then I'll have plus the sum of the rest, right? Because after I take these off, they all start at n equals 1. So n equals 1 to infinity of the first thing, n plus 2, then n plus 1, a sub n plus 2, minus 2n, a sub n, plus a sub n, all that times x to the n. Okay, so this equals 0. Now, what I have here is a power series. All of this stuff equals 0. But if we look at this, this is actually the x to the 0 term, right? And so this is still a power series. This first term just didn't quite fit the same mold as the second term. So the first thing I get is that 2a2 plus a 0 is equal to 0, which means that a2 is going to be negative 1/2 a 0. So there's my first recurrence relation thing. And then the next part, so then the rest of it equals 0 as well. So I get n plus 2, n plus 1, a sub n plus 2 minus Actually, let me say plus, and I'll say negative 2n plus 1 a sub n. So let's write it that way. Equals 0. Now, we're going to always solve for the bigger one, right? That's going to be the way that we want to go here. So let's do that. I'll get positive 2n minus 1 times an plus 2, so subtract that over, and then divide by the stuff in front, n plus 2, n plus 1, and here is my recurrence relation. And so now I just need to play the game. How much room do I have? Well, I got plenty of room. Now I just need to kind of play the game of what I do with all of the n's, right? So these n's start at n equals 1 and so on, right? That's where that recurrence relation starts. So let's do that. N equals 1, that will be a sub 3 equals, let's see, 2 minus 1 is 1, and 1 plus 2 is 3. Okay, so this one is the same as this one, and that is 1 less. So that's going to be 3 times 2 is 6 times a 1. Okay, good. Now let's do n equals 2. That's going to be a 4 times what? Equals what, I'm sorry. And that's going to be a 2. And n is 2. 4 minus 1 is 3. On the bottom, I get 4 times 3. Then n equals 3. I get a 5 equals, let's see, 1, 3, 6, 5. And then that's going to be 5 times 4, a 3. Okay. Let's just go ahead and simplify them. So it's going to be 5a3 is that one right there. And so 5, 4, 3, 2, a1. N equals 4 gives me a 6. And, while I have this here, a2 I have up above. Let me move this down. This is 3 times 4, 3, 2 with a negative 1 on it, a0. Interesting. Okay, then n equals, 4, I didn't 4 yet. This is going to be 1, 3, 5. It's going to be 7. Right, 2 times 4 is 8 minus 1 is 7. 7 over 6 times 5, which is going to give me a 4. And a 4 is this thing above, so that is 7, 6, 5, 4, 3, 2 times negative 3. Interesting. A0. And so on and so on. It looks like we're headed for a pattern here. Let's just do one more. Well, maybe we'll just call it good there. So it looks like I have in the odd n case, these are going up by 4, right? So this is going to be okay, I'll do one more case. N equals 5. A7 is going to be 7 times 2 is, 7 times 5 is 10 minus 1 is 9. Yeah, so it looks like we're increasing by 4 on the top over 7 times 6 times a 5, which gives me this one here. So 9 times 5 times 1 over 7, 6, 5, 4, 3, 2 of a 1. All right, this is getting pretty big. We can kind of see the pattern, though. These all have a negative sign on them. So on the even side, we have a negative sign, and then it goes from 3 to 7. The next one will be 11. Here I go 1, add 4 to 5, add 4 to get 9. We're increasing by 4 and multiplying those on the top. That is kind of a weird one to write down. With the n plus 2 factorial on the bottom, the same thing goes here. At this point, we're going to cheat just a little bit, okay? So my differential equation is a second order linear differential equation. I know that there are going to be two functions that form a basis of solutions, and those functions are y1 and y2. And that y is a linear combination of those, so c1y1 plus c2y2. Here's what I know the answer looks like, and this whole thing is the a sub n x to the n, right? All right. Well, looking back here, what I know is that one of them, all of them have a naughts in them, and the other one, all of them have a ones in them. Those are the two parameters. And so it's not really C1 and C2, it's really my A0 and my A1. Those are the two things. Okay, those are my two parameters. And so what I can do is say, well, like, let this one be 1 and this one be 0, and that will kind of isolate these things and tell me what the y1 is. And then I can let this thing be 0 and this thing be 1, and it will kill the other one and let me know what y2 is. Okay, so that's our plan. And then we can kind of go through and just look at this and start calculating them. So we're going to say, well, let A0 be 1 and let A1 be 0. So then my y, which is the sum of a sub n x to the n, okay, so I have 1x to the 0 plus, okay, now we can go back and start looking at our recurrence relation here. So I get negative 1/2 times 1 x squared. A1 is 0, right? So I skipped that one. And then the x cubed, well, the x cubed is on this one, which has an A1 in it, and so it goes to 0. So the next one is x to the 4th, and that's plus, so that's A0, that's A1, that's A2, where's A4? So A4 is going to be negative, the 3's cancel, and I get negative 1/8. Right? So that's going to be negative 1/8 x to the 4th plus no x to the 5th. What is a 6th? We'll just do one more here. A 6 is going to have this one, and we can do a little bit of canceling here. The 3's cancel, and I get, oh, that's kind of yucky. Negative 7 over, can I multiply that number that big? 240. Actually, I can. How about that? So negative 7 over 240, x to the 6th, yada, yada, yada. Okay, now let's reverse it. So A0 is 0 and A1 is 1. And so that gives me my y2. So that has no x to the 0 plus 1x to the 1. Okay, so there's my A1. I'm going to skip the A2 because A2 is a function of A0, so I don't need that one. Then A3x to the 3rd. So what's A3? Well, A3 is this one. That's just 1/6 A1, so there's a 1/6 there. Plus, I can skip the 4. I'll go to A5 next, x to the 5th. So x to the 5th is this one. Those cancel. 4 times 3 times 2 is 24. So 1/24. Plus, I can skip the 6th. We can go with A7, x to the 7th. And this might be getting too big for me to do here. Here's my A7, and I have 9, 5, 1. The 5s cancel. And what else can I do? 9, 5, 1, 7, 6, 5, 4, 3, 2. It's going to be kind of yucky. Those go away. Those go away and leave a 2 there. So that gives me 8 times 7 is 56 times 2 is 112. So 1 over 112 plus dot 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 dot. Okay. So I have found two functions, y1 and y2, so that y is a linear combination of those using power series. Okay? So there we go. I found my two solutions. If I wanted some kind of approximation, then what I could do is I could find the first so many terms of this thing and add those two together. And so y would equal this plus this plus this, 3, 4, 5, 6, 7, right? And all of these would have C1s in them, and all of these would have C2s in them, okay? All right, let's do the next one. Find the series solution around c equals 0 for the following differential equation. So I have x squared plus 1 y double prime minus 4x y prime plus 6y. Now, this is almost an Euler-Cauchy, right? If it weren't for that thing right there, this would be an Euler-Cauchy equation. So let's find out what happens here. I think we probably know already what all of them are going to turn out like, so let's just write it down. X squared plus 1 times n equals 2 to infinity n minus 1 a sub n x to the n minus 2. Again, just look at the previous problem. Minus 4x n equals 1 to infinity n a sub n x to the n minus 1 plus 6 n equals 0 to infinity a sub n x to the n. All right, and all that equals 0. I have a bit of good news here in that this one, when you plug it back in, bumps it back up to n, and this one bumps it back up to n. I just have this one kind of thing here bothering me. So let's do all these here. I'm going to put each of them in. I'm going to split up this first one into 2. So let me send in the x first, and that gives me n equals 2 to infinity n minus 1 a sub n x to the n. Okay, that's sending in the x squared, plus n equals 2 to infinity n minus 1 a sub n x to the n minus 2. So that's the 1, right? Then I have minus, I'll send in the 4, n equals 1 to infinity 4n a sub n x to the n, plus sum n equals 0 to infinity of 6a sub n x to the n equals 0. All right, I have this one to fix, so we'll save me some writing here. I'm sorry if you're following along on paper. Let's fix that one. Okay. I need this to be x to the n, so n is going to go up by 2. This is n plus 2, n plus 1, a sub n plus 2. And the n will begin at 0. All right, next. We are going to cheat a little bit more because this one can start at 0 with no problems, right? And this one can start at 1, no problems. Oh, can start at 0, no problems. So I can cheat on this a little bit, and I can make both of those 0 because of the terms that are in there, okay? And again, this happens a lot on the derivative ones because of the way you have the n and the n minus 1 in there. So I'm good to go. All of those start at 0. They all have x to the n, and so I get to write down some gigantic expression. With x to the n's. All right, n minus 1 a sub n plus n plus 2 n plus 1 a sub n plus 2 minus 4n a sub n plus 6 a sub n. Good. Now I have all of this is equal to 0, so let's write that down. I'm going to do a couple things here. Let me just kind of start expanding this. I have n squared minus n, a sub n, plus, I'm not going to factor that one. I'm not going to distribute that one. N plus 2, n plus 1, a sub n plus 2, minus 4n, a sub n plus 6, a sub n equals 0. And all of the a sub n things will go to this side. So I'll have a sub n plus 2 is equal to, all right, negative n squared plus n plus 4n minus 6, all of that times a sub n divided by n plus 2, n plus 1. Okay. Now how does that work on the top here? Let's factor out a minus sign. That'll make our factoring go a little bit better. Minus n squared. That made 5, so minus 5n plus 6. So then a sub n plus 2 is minus, that factors n minus 2, n minus 3, n plus 2, n plus 1. A sub n. I have more room? Good, I do. All right. Well, we can start with n is 0 on this one. And let's just start it down here. When n equals 0, I have a2 is equal to negative, negative 2, negative 3, 2 times 1, a0, which is negative 3, a0. When n equals 1, I have a sub 3 equals, I need to see this down here lower. Copy, paste. All right, when n is 1, I get negative 1 minus 2 is negative 1. 1 minus 3 is negative 2 over 1 plus 2 is 3 and 2, a 1. All right, what cancels here? So those, and I get negative 1/3 a1. Now let's try n equals 2, so a4. And when n is 2, I get negative 0 times I don't care over I don't care times I don't care, a2. So that is just 0. Now, what about n equals 3? That's a5 equals negative 5 minus 2 is 3. I'm sorry, not 5, 3. Don't know why it's going up too much. 3 minus 2 is 1, but then 3 minus 3 is 0. So that's 0, and now I don't care about these two. They're not 0. I do care that they aren't 0, but they aren't here. And so I get 0 times a3, which is 0. Now, Our recurrence relation here involves n plus 2 and n. If I find two consecutive that are 0, then the next one will be a constant times 0, which is 0. Next one, constant times 0 is 0. Next one, constant times 0, and 0, and 0. So this is all of them, okay? I am done. I have my A0, I have my A1 and my A2, and my A3, and that's actually it. So y looks like, okay, let's write it down. I have A0 x to the 0 plus A1 x to the 1 plus A2 x squared plus A3 x cubed plus the rest are 0. That's it. And I know the relationship between these. I can erase that. Plus A1x plus, now what is A2? A2 is negative 3A0 plus A3 is negative 1/3 A1 x cubed. And so y is going to be A0, right? That's going to be my first parameter. 1 minus 3x squared plus A1 times x minus 1/3 x cubed. Right, so take that one, that's 1, take that one, take the a naught out of it, put the x, and then this one, take the a1 out of that. And so here I actually have the solution is a cubic polynomial with parameters a1 and a2 if I had initial conditions. And there we go. Speaking of initial conditions, what happens if we had some of those? And this will be our last example here. Solve the initial value problem, blah, if y of 0 equals 3 and y prime of 0 equals 0. Now, we're going to just kind of skip to the end here, right? So suppose that this is one of my y1 and this is my y2. What I know is that y is going to be ay1 plus by2. That's what I know. Okay, this is going to be, because this is a second order linear differential equation, and I know my y1 and y2. And we can find these using the techniques that we found earlier. So, what do I know? Well, I know that y of 0 is what? So, a times y1 of 0 plus b times y2 of 0. Now here's where 0 really helps, okay? Like if it was y of 2, then we would be, let's just say, very unhappy. But because it's y of 0, y2 of 0 is 0. So that whole thing goes away. And y1 of 0 is actually just 1. So that's a times 1. Because all of those things go away. And so this is pretty nice in this one circumstance. Y of 0 is equal to 3, so there we go. I know what my a value is. A is 3. Y prime I'm going to have to do just a little bit of work for. So y prime is, of course, a y1 prime plus b y2 prime. And that is, so that thing goes away, and I get a times negative 8x plus 16/3 x to the third plus da 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 da, plus b times 1 minus 3x squared plus 1/2 x to the fourth plus da 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 da. All right, and now that's my y prime. So then y prime of 0 is equal to what? Well, all of those go away, and all I'm left with over here is just b. So in this case, this is equal to 0. So I have b actually equals 0. So I know what my final, what my particular solution is. It is y equals 3y1, which is 3 times 1 minus 4x squared plus 4/3 x to the 4th plus ... And that is it. We are going to call it a wrap for this section and this chapter and this class. You made it. Congratulations. I will say see you next time, but there won't be unless you take another class from me. And maybe I'll see you then. Okay? Take care.